Okay, everyone, welcome to this OWL's seminar. Nice to see so many people here, and it is a great pleasure to introduce the speaker of today, Mikołaj Bojańczyk from Warsaw University. Mikołaj needs no introduction. He is a prolific researcher in the theory community and has had many awards and accolades, and I'm sure he will tell us lots of cool things about polyregular functions. So Mikołaj, the floor is yours.
Thank you very much, Alexandra, and thanks a lot for this invitation to you and Pavel and Jamie. Well, as Alexandra said, I'd like to encourage you to interrupt me at any moment. I have very few slides, and 3 of them are empty. So we've got time. So what I'd like to talk about today is, well, it's automata because the only thing I know how to talk about. It's about string-to-string transducers. So this is like automata, but they input a word or a string. I think if you're doing transducers, you're supposed to say string instead of word, and it makes you sound more like Perl or something. But instead of saying yes, no, they output something. And then there are many different machine models for such strings-to-string transducers. In fact, they're equally old as yes-no automata. Actually, automata started out not as being yes-no devices, but then in the Scott Rabin paper, there's like a remark which says, there's these automata that have been discussed recently, and they have these complicated output things, and but we just replace it by a yes/no value, and the theory is the same. So that happened then. But a few years later, I think Dana Scott relented, and he wrote a paper in which he wrote that, I mean, amongst other things, that in his opinion, when one looks at devices such as automata, it is not necessarily the languages which are the more important concept, but the functions that they recognize. And this is the perspective of this talk. So it is about automata which recognize functions. Now, the word automaton is viewed here very Catholically. So it's just anything which is somehow finite state. And that's, of course, subject to interpretation, but you know it when you see it. So let me get to the point. I will begin with one class of functions that has been rather popular recently, well, in the last 10 years, say, in the automata and transducer community, which is called the regular functions. To be honest, I think it's an abuse of the name, because it's a holy thing in automata theory to call something regular. So there's only one notion of regularity. So if you call your thing regular, that's a bit, but anyway, they did it, and we're stuck with that name. So let me explain what are these regular functions, and I guess that a very nice one that I will use to explain is the following function. I'm not sure if you can machine learn it from the example, but what it does is it inputs a word and it outputs all of the, and I wrote it wrong as well, so you cannot machine learn it. It's supposed to output, but that's, well, maybe you should be able to. It outputs all of the prefixes of the word, one by one, but in reverse order. So it should be, the output should be 3, 2, 1, that's the longest prefix, and then 3, 2, and then 1. Okay, that's what it's supposed to be. So this is an example. No, I'm not making any sense. I confused that. I'm sorry. It is a correct example. I just confused the parts of the talk. This function is a different one, sorry. It's supposed to be the following. You output the word and then the reverse of the word. Okay, so the example is correct. I apologize. So this function is going to be, I give you several different kinds of devices, all of them informally described, which are capable of capturing this function, which inputs a word W and outputs W followed by the reverse of W. The first one, which is the most classical one, it dates back to the origins of automata theory, is a two-way deterministic automaton with output. So I guess, well, you see the name, you know what it does. Huh? So it's like the usual two-way deterministic automaton, so like a Turing machine, but without any tape, any work tape, just which works just on the input tape. And then once in a while, it decides to append an output letter to the output. Okay. So you can obviously do this function because you begin at the beginning of the word, you scan it left to right, then that gives you W, and then you scan it right to left, that gives you the reverse of W. And then, you know, you could scan it maybe 5 times and you could copy the word 5 times. That's the kind of things you could do. So that's one of the oldest transducer models. And I will now discuss a number of other transducer models which are equivalent to it. And because there's so many models which are equivalent to it, then the class of functions which arise this way seems to be a very natural class of functions. And that's why people call it the regular functions. So so that was the two-way automaton. So now the second model is something called Monadic second-order transductions. So this is something that originates originally they were described for graphs and general structures, but they make sense already and they're very interesting already for such simple structures as words or strings. So what is this? I'll just give you an example. I won't go into the syntax. The idea is that you describe using formulas of a logic, and in this case, it's monadic second order logic. It's the logic that all automata people use. You describe how the output word arises from the input word. And what you do is you describe what are the positions of the output word by representing each position of the output word in some position of the input word. Maybe you're allowed to copy the input word a few times. So in this particular case, I will copy every input position twice. I will have 2 copies of it. And then I will use logical formulas to say what is the order on these copies and what are their labels. So I write something like every position of the output word is, well, it's either, there's 2 kinds of positions, one which originate from the first copy of the input word and one which originates from the second copy of the input word. And then you say how they're ordered. So you say that all first copies are before all second copies, but within a copy you use either the forward order or the backward order, depending on which copy you're in. So then you formalize this using formulas. The logic in question is MSO, monadic second order logic, because this is the logic that corresponds to automata. And the functions which can be described this way are what are called MSO transductions. So what is important here, and this will play a role later in my talk, is that every position of the output word originates in one position of the input word. And maybe there's like k copies. In particular, by definition, it follows that the number of output positions is at most k times the number of input positions, because it's just in this, it's in the syntax. So they will have linear growth, these functions. Another model, so one of the starting points in like the recent resurgence of interest in transducers is this wonderful result of Engelfreich and Hogebaum, which says that these 2 models are equivalent. And so it's one of those nice theorems where you have two models which look kind of different, and the proof is non-trivial, but they describe the same functions. So there's something going on here. It's a good class of functions. Also, it has other good properties. It's closed under composition, so composition of functions, which is rather easy to see on the MSO transductions, but it is not so easy to see on the two-way deterministic transducers. This is like if you try to think about it, it's not at all clear how to do it. You try to compose one two-way device, and then on its output, there's another two-way device, and how to fold that down into a single two-way device, that's not at all clear, but it's true. And it follows, for example, from this equivalence. But then people continued to study this, and there were other models which cropped up, and I'd like to describe some of them here. One which I think is very important is something called streaming string transducers, which was introduced by Rajiv Allur and Pavel Czerny in 2011. And the idea is as follows. It's a one-way device, okay? It's not a two-way automaton. So two-way automata are well known to be a nightmare to work with. It's very hard to prove anything about them. So anything that you prove about two-way automata, what you typically do is you first convert them to a one-way automaton, and then you do your work. So this is something that was done here. So they introduced a model which turns out to be equivalent, which is a one-way device. So how does it work? You scan your input left to right, deterministically, and you have a certain number of registers, which, let me zoom into it maybe, a certain number of registers which you use to store, the idea is pieces of your output. So if I want to do my function which where the output is W followed by W reversed, what the obvious thing to do is that I will have one register to store W, and I will have a second register to store the reverse of W. So whenever I use I see a new input letter, I append it to the W register and I prepend it to the W reversed register. So that's the kind of things you're allowed to do. Whenever you see an input letter, you're allowed to manipulate your registers by appending letters to them and maybe appending registers to each other. There is an important restriction which is called single use, and this is actually very interesting, which says, it has a formal definition, but it sort of says that when you create your new registers as a function of your previous registers, each previous register can only be used once. So you cannot, for example, have an update which says register R becomes register R concatenated with register R. If you had that and then you would keep on doing it, you would have exponential growth, for example. And so this single use restriction is there, and it seems to be somehow related. Well, it guarantees that the output size is linear, and it seems to be kind of connected to some linear things. And there's a research on this topic that I will linear types in the sense of linear logic, and there's some research in this direction that's going on recently, which I think is very interesting, but I don't understand. Okay. So that's another model, and this model has been it's a very simple model, and it's attracted a lot of interest, and people are starting to look at these things intensively recently. So there's several other equivalent models to this class of functions. I will not describe them in detail. One of them is this is also by Allure and collaborators. It's a notion they devised a notion of regular expressions, where like you say how you can construct more complicated transducers from simpler transducers. Like, for example, you can say concatenate two transducers. And that would mean that if you have two transducers, F1 and F2, then their concatenation would be a transducer which first produces the output of F1 and then concatenates to it the output of F2, like pointwise concatenation. And then there's some kind of Screeny star, but there's quite a lot of these things there. So the number of operators is quite large, but it's a thing. So there's a characterization of that kind. Another one that is I find personally very interesting is that there's a kind of Krohn-Rhodes decomposition. So this is meant to be similar to the name of the Krohn-Rhodes theorem. And what it means is that you can show that every transducer of the class that I'm discussing right now, which has all of these many definitions, can be decomposed into a composition in the sense of composition of functions of certain basic transducers. And there's like a list of like 5 prime transducers that you can use. And this is also very useful. But this is not something that I want to discuss in this talk. What I want to discuss is another presentation, which is something that we did together with Krishna and Nordavio, which is called regular list functions. And this is meant to be an alternative to the regular expressions. But it has more of a functional programming type kind of character, as you will see in a moment. And the idea is that it, as opposed to the regular expressions of Rajiv Allure and his collaborators, it is very strongly based on function composition. In fact, in the regular expressions of Rajiv Allure, function composition is not one of the combinators, which is kind of amazing. I mean, that's the whole point of doing functions, that you can compose them. And but it's not one of the combinators. I mean, you can add it because the class is closed under composition, but it's not. It's a derived operator. It's not one of the fundamental ones. So for regular list functions, the idea, which is very much in the spirit of the Krohn-Rhodes theorem, is to see how much power we can leverage from the fact that we can compose these functions, which in my perspective is the whole point of studying automata that create functions so that you can compose them. But of course, there's other perspectives. So, but this is, well, it's my talk. So let me describe these regular list functions to you. So it works as follows. So let's suppose my final goal is to describe string-to-string functions. But as intermediate objects, I will use functions which input pairs of strings or strings of pairs and stuff like that. Those will be intermediate things that will appear. So I will have data types, which are constructed as follows. Every finite set is a data type. And then you have this co-product or disjoint union, you have product, and then you have the list constructor. Okay, so, and then you can apply these constructors many times. So you can have like a list of pairs, of lists, of whatever. So these are my data types, and the functions will be from one data type to some other data type. And which ones do I care about? Well, it's described as follows. I first give you a certain set of basic prime functions. And then I will say that beyond that, they're closed under certain combinators, most importantly, function composition. So what are my prime functions? So some of them, can you see this expression?
Yep.
Because on my screens, the zoom thing is obscuring it, but I guess you don't see that good. So first of all, you're allowed to have every constant function. No matter what is your domain or codomain, as long as your function is constant, that's fine. That's I would say a rather benign thing. You could add that you have you also have the identity function on every type, but that in fact would be a derived function. That's another kind of very benign function that you might want to have. Then we have the induction definition of lists, inductive definition of lists. So if I have a list, then I can decompose it into the head and the tail, or otherwise say that it's empty. Okay, so there's both of these functions in both directions are prime functions. So these are two functions here. Well, it's a family of two functions for every choice of tau. Okay. Another one is this basic. I hope I didn't make a mistake. This distribution of co-product across product. You could have it both ways, but actually the other one is derivable. So these functions are meant to be like, well, obviously you need to have them. Yeah? There will be like 2 or 3 more interesting ones at the end. Then I have the projections and the co-projections. There are nothing surprising here. Now we start to get a little bit controversial. Reverse, that's an atomic function. Okay. It's actually kind of interesting what happens when you eliminate reverse. And to be honest, I don't know. But I think there's an interesting class arising there. I mean, okay, if you remove reverse, then you need to do like have the dual of head and tail. So like you look at the list from the other end to restore some symmetry to the things. But that seems to be an interesting class. But reverse is there. Then you have this, well, this monad structure of lists. So you can concatenate a list of lists into a list. The list unit, so from a letter to a one-element list is derivable here. That's it's using the first function. That's not so hard to see. And then there's maybe like 2 more functions which are kind of funny. This one is maybe, it's one of the functions that I'm not sure if my criterion for and it's not just mine. I mean, I guess it's Phil Wadler's as well. A criterion for a good function is one that if you just see the type, you know what it is. So I think that most of the functions that I wrote here have this property, and I think in a provable way. Well, except for the inductive definition of lists, because you don't know if where is the head? Is it like at the beginning, at the end, or is it in the middle? And another one is I guess reverse. That's not clear that it's reverse if you just look at its type. And well, block. I'm not sure if you can guess it from is it clear to, is there anybody here who has not seen this function before and can guess what it does from the type? Please just offer, I don't know, Alexandra, you tell me, what do you think it does?
What do I think it does? It takes each of the 2 other functions, just repeats them over and over again.
I don't know. Okay, so thanks for so this is okay. See, I must have been a bit confusing then. It does not input functions.
Ah.
The input is a list over a disjoint union of two alphabets. They could be finite, they could be have further structure, but it's a list, it inputs a list over the disjoint union of two alphabets. I think it's,
okay. And the output is just a list over the disjoint union of words over those alphabets? Or?
Yes, so there's several functions of this type that one can imagine, but the one that I have in mind is this one. Like imagine that your two data types, one is letters and the other is numbers.
Actually, Tom Irshowitz, I think, replied the right answer in the chat.
So what it does is it groups same type elements into maximal blocks. I mean, there's also the name of the function, which can kind of help, I guess. So that's a weaker, more sociological criterion. You look at the type and you look at the name of the function and you know what it does. Okay, so these are the functions. And unfortunately, there's like one more, which is a little bit of an ugly duckling in this group, which is products of groups. So what this does is that for every finite group, so it's an infinite family of functions which is indexed by finite groups. So for every finite group tau, you have a function which does the group product, but so the most natural one would be it inputs a list of group elements and it just multiplies them and gives you one group element. But this one, what it does is it takes every prefix, it multiplies it and it appends it to the list. Okay, so it's a length preserving function. So for every position in the input list, you output you multiply all elements up to and including that position, and that's what you put in your output list. Okay, so this one, yeah, that's a bit of a disappointment. It's a function that's present in the Cron-Rhodes theorem. It's some kind of yeah, it's literally one of the prime functions in the Cron-Rhodes theorem, and that's why it's here. But actually, it turns out that if you eliminate this function, then the class of functions that you get is actually very well behaved, and it corresponds to first order logic as opposed to monadic second order logic, which people who are experienced with this kind of thing would be expecting, because that's the usual pattern. MSO is first order logic plus groups, and that happens here as well. Okay, so these are the regular, the prime functions. And then there's the combinators, which say, how do you construct new functions based on previously constructed functions? And well, they're like, some of them, most of them, well, they're meant to be obvious. So it's like a cases thing. So, yeah, that's, if you know what to do for tau 1, you know what to do for tau 2, then you know what to do for tau 1 or tau 2. And then the dual one, so you can map an input to both possible outputs. This is the most important one. You have function composition. And then you can, it's like the functorial version of map. So you can lift a function on letters to a function on input strings. And what we show is that these functions are equivalent to the others, and that gives yet another perspective on this class of functions. Okay, so this concludes the first part of my talk, where I describe a functional programming kind of way to think about these transducers. So, and well, the alternatives are automata, either two-way or one-way of registers, and monadic second-order logic transductions. Pavel, go ahead.
Hi, I'm just wondering about these groups. So I'm not one of these people who knows that to get from first order logic to monadic second order logic you need groups. So can you just explain? I mean, like, it's super clear. I just don't understand. Like, can you give a little example where one might use a finite group or something?
Sure. So well, one is the parity language as a regular language. So you input a list of letters, which are either 0 and 1, and your output is 0 or 1, which is just that, well, literally the group product in the two-element group. And so this is, well, because this is a function with yes, no outputs, so 0 or 1. It's a language, and the parity language, it cannot be done in first order logic. And this is like a classical theme in automata and logic that because there's a cycle, then you cannot do it in first order logic. So that's something that has been established, I guess, by Schützenberger, I mean, in some senses earlier, that counting parity is a classic thing that you cannot do in first order logic. So Z2 is a cyclic group, and there's some more fancy groups like, you know, 5-element symmetric group, and then you need more and more powerful logics. But in the end, it's a monadic second order logic that you need. So this is it's a theme that has been quite well explored in the automata literature, that what we do as automata people and logic people is when we decompose something, we stop at groups. I mean, you know, there's a theory of groups, but we don't do it. We just say it's a group, we're done. You know, let Ser take care of it now, huh? And that's the modus operandi here.
I was thinking kind of operationally. So I was, you know, in terms of these, since this class is going to have the same power as these two-way automata and these transducers with registers that you described previously. So I'm just trying to think of an example where I would need this additional structure of a group, you know? Is there some kind of obvious?
No, well, I think it's, yeah. So it's a very good question, Pavel. I mean, it's, I guess that what an alternative way would be that instead of adding groups, I would add some kind of iteration principle to, and I don't want to do that because I think it would be easier to do that. And that's why I don't want to do it. But it's actually, so that gives you I mean, it's hard to explain right now, but otherwise you would be left with an automaton. What I want to do here is I want to decompose it using very basic operations such as function composition into things which are atomic. And if my combinators would include some kind of iteration or fixed point mechanisms, it would be much, much easier to get decompositions, and hence these decompositions would be of less value. Yeah, that's maybe, but it's hard to explain just like that right now. But another important point is that it's also, the groups are there so that it's meaningful to say that let's not have them. And actually the class of functions which arises if you disallow the groups, which is in my opinion a more natural class of functions. It also admits these multiple different characterizations. So in the MSO, you need to say that it's first order logic. In a streaming string transducer, you need to impose some monotonicity conditions. And in two-way deterministic automata, there's also something you can do. And in the Cronrose decompositions, there's also something you can do. It's there. And in fact, the first order fragment, the group free fragment, is the more interesting class in a sense that this, I mean, again, one would need to explain what it is, why that is exactly. But any theorem that you prove for the first order fragment is going to be a stronger theorem than the one that you prove for the MSO fragment. So in fact, actually the groups are also there to say, what if we don't have them? And it turns out that if we don't have them, actually very interesting things happen. There's another question, I think, by Paul Taylor.
Oh, Taylor,
well, I was just looking at your system of functions from the point of view of either a type theorist or a categorist. And I would, you know, I mean, there's a relevant piece of category theory here called an arithmetic universe. But even from a type theory point of view, one would expect recursion, primitive recursion over the lists. So that's a theorist's point of view. Now, there seems to be something rather ad hoc and arbitrary about the way you cut off your functions.
Is there a question? Or, I mean, no, that's.
I'm just wondering. Maybe you will come to this of you know, what is the, as it were, theoretical motivation for cutting off your functions well short of being able to do recursion over lists, which is what a type theorist or a categorist would expect of this
Yeah.
type
So
system.
this is related, I guess, to the well, my comments when I meant to Pavel's question, which is why don't I have some kind of iteration mechanism such as recursion? And there's several answers to it. First of all, one would have to be rather careful to have recursion that stays within the class of interest. That would be doable, but that's item one. Most natural recursion ideas would go outside the class, and it would go significantly outside the class. It would give you functions of exponential and non-elementary blowups. But I think that there should be recursion mechanisms that deal with that, and there are in fact papers of that kind. But the second comment is that it is a design goal for me to not have recursion. I think the result, which says that you can decompose every function into these prime functions without using recursion, is a stronger result than one which would use a very strong mechanism of recursion. And well, so you might ask, what do I get out of it? So here's an example. Suppose that I have a function in this type. Then what you can show is it's rather easy to see. Say I avoid the groups. And as I mentioned, it's a more important one. Then you can compute the output using a constant depth circuit, like in the class AC0. So functions which arise this way one can show that they belong to the class AC0 if I omit the groups. And that kind of result, it is if I would have recursion, that would be it would be hopeless to prove this. So these kind of decompositions this is the direction that I go into. I want to avoid recursion. I mean, I'm not saying that people who do recursion are doing a mistake, but it's just not what I'm doing here. Is that helpful somehow?
That's a legitimate point of view. What I was looking forward to is you're demonstrating that this class of functions is is of interest. I mean, I can see it's of interest from a programmer's point of view, right? But I was wondering whether there was a theoretical.
Okay. I hope that you will
carry on. Let's end the interruption.
So let me I hope that you will be more interested in the second class, which is the main topic of my talk. Right. But even for this one, I would hope that it would be interesting to some people because, well, I mean, it's not my class. I mean, these are other people's results mostly. Okay, so let me now go beyond these regular functions and to the title of my talk, which is polyregular functions. And well, I guess you can guess from the name, what is the point? They're supposed to be kind of polynomial. And what polynomial do I have in mind? Well, if you look at the regular functions, they will have, and I mentioned this already, but I'll say it maybe once again, they will have linear size increase. Okay, so for example, I mentioned this for the MSO transductions. Here's another argument. If you have a two-way automaton and it has k states, then every input position will be visited at most k times, because otherwise it would enter an infinite loop. And therefore the length of the run is at most k times bigger than the length of the input. And since, so that means that the size of the output is going to be at most k times bigger than the input if you assume that every transition produces at most one output letter. So they will have linear size increase. So if I were to redesign the terminology, I would call the function class of functions that I have described already as the linear regular functions. And the point of the work that I'm presenting to you is to say, well, how do you go to polynomial functions? Is there a robust class of functions which is kind of finite state but has polynomial size outputs? And that's the point of polyregular functions. So let me describe it to you now. So here's the example that I confused in my head. So what it does is you input a list, and then you output all of the prefixes. So you start with the full length prefix and they get suffixes, I think. You take all of the suffixes that they get shorter and shorter. And each one is output in reverse order. So it's supposed to combine all many features here, okay? So you first go 4, 3, 2, 1. That's the full suffix in reverse order. Then you go 4, 3, 2, and then you go 4, 3, and then you go 4. So the length of the output is, well, roughly n squared. So it's quadratic. Okay, so the first model that can do this, it's something that was there before in the context of trees, but I say let's look at it in the context of weaker context of words. It's something called deterministic, two-way deterministic automata with pebbles. So the idea is as follows: you have a two-way automaton, but it's allowed to put pebbles, but there's a fixed bound in the automaton k, which is fixed in the syntax of the automaton, on your input to remember some positions. And then there's an important thing, which is that these pebbles need to behave in a stack discipline. So like if you have like the oldest pebble and then the more recent pebble and so on, you can only move, if you move a pebble, then you need to discard all of the more recent pebbles. So you can think of like the oldest pebble moves very rarely and the most recent one moves a lot. Okay, that's the idea behind this model. That's definition 1. But the point is that there's like definitions 2, 3, 4, and 5. Okay, and they're all equivalent. So here's another model, which is, oh, I think I should have zoomed in, but it's called, let me check if it, no, there's an error in my slides. It's called for transducers. So what does a for transducer do? Imagine a for program like Python or something. And can you see the letters on my slide? Are they too small?
I think they are okay.
Okay, thanks. I was supposed to zoom in, but I think I made a mistake somewhere. So what you do is you first loop through all positions in the word, and then in first to last ordering. Okay, and these will tell you what is the prefix that you care about. And then once you have fixed which prefix you care about, this is position X, then you loop for all positions in opposite order, from last to first. And then if you're still to the right of your of X, then you output the input position. Okay? Is this program clear? It's meant to give the function that I described. So that is roughly, this example illustrates the entire thing that you can do. So you have 4 loops. There's no while loop. There's just 4 loops. And the 4 loops, well, they just range from left to right or right to left. Okay, you cannot, so if you think of a variable in a for loop as a pebble, then what you have is that your pebbles can go either only right to left or left to right, but they cannot move alternate directions, which is the whole point of two-way automata. They're not allowed to do that, okay? So it is rather easy to translate a for transducer into a k-pebble automaton where the number of pebbles k is the number of nested for loops. The opposite translation is also possible, although if you start with a k-pebble automaton, then you get a for transducer which has much more nested for loops than k because of this directionality thing. Already a k equals 1 pebble automaton, also known as a two-way automaton. It is, if you think about it, it's not at all clear how to translate it into a for transducer because it could alternate directions a lot of times. And how do you deal with that? But it can be done. Okay, so that's one model. I think my example covers almost the entire syntax of for transducers. There's one more thing that I did not write, which is Boolean variables. So you're also allowed to have Boolean variables which store values, well, true or false, and then you're allowed to read and write to them in an arbitrary way. But the loops, so there's 2 kinds of variables, position variables and Boolean variables. The position variables are bound by the loops. That's how you create them. You're not allowed to write to them in any way. Just you get to loop over them. The Boolean variables you can read and write to them in an arbitrary way. That's a for transducer. Then the second thing is I'm a bit worried that I cannot zoom myself. Okay, well, I'm sorry, the font is so small. Then yet another equivalent model is something called MSO interpretations. So don't read into the text, just listen to me. So in an MSO interpretation in the linear case, what you had was every output position would be interpreted in one input position. Maybe you could have several copies, but that's an insignificant thing. And that would guarantee that your output size would be linear in the input size. Here, what you can do, and this is actually what the classical notion of first order interpretation does, every output position is interpreted in a tuple, in a k tuple of input positions. So you think of your output positions as k tuples of input positions. And then you have a formula which tells you which k tuples of input positions actually are used in the output. So it says this one is used, that one is discarded. And then you have another formula which inputs two k tuples. So it has two k free variables, and it tells you, is this k tuple before that one? And I guess there's another one which tells you the label of it. And all of these are MSO formulas. And it's a very natural definition, but nobody's ever done it, and there's a reason. Because if you look at it for the first time, it's going to be obvious that it doesn't make sense. If you've worked with MSO, you will immediately see that such MSO interpretations, if your input is like a word, then you can output a grid, and well, everybody knows if you have a grid, then you're done. But actually, it's not true. It turns out that this notion is well behaved. It's kind of unexpected if you've worked with these kind of things, and it's closed under composition, which again is very strange. And the reason is that nobody would ever think of composing two such things, because if you imagine two such interpretations, and they're non-linear, so they're like they're quadratic, then both of them say are quadratic. Then if the second one uses MSO quantifications of positions over the intermediate string, then positions of the intermediate string are pairs of positions in the input string. So quantification, MSO quantification over positions of the, if you're trying to compose two functions, the quantification in the second one would correspond to quantifying over sets of pairs of positions, and that's clearly something you cannot do in MSO if you're familiar with MSO. But it turns out that for some very strange reasons it works, and it's a very strange thing. And there's another description of this class, which is in the spirit of Cron-Rhodes. So let me describe it to you. It says that you take the regular functions. That's one kind of prime function. Every regular function is allowed. And then you close it under composition, so you can compose functions. And then you add just one extra function, which is this squaring function that you see at the bottom of the slide. It inputs a word, and then it copies it. Well, if the input word has length n, it copies it n times. But for the ith copy, you underline the ith position. Okay? And that's the only extra thing that you need. And then if you compose, so you take a composition of functions, such that some of them are squares, some of them are regular functions as defined before, then actually you will get exactly the polyregular functions as described in this slide. And because the class of regular function itself is subject to a Cron-Rhodes theorem, which decomposes them into smaller pieces, then you get a full Cron-Rhodes theorem if you plug it in. And then there's the last thing, and which is in the spirit of these functional programs. And this is something I wanted to describe to you. So what is this? So it's the same thing as the regular functions as I described before, but you add lambda abstraction. You have no fixed points, no recursion, but you do add lambdas, okay? So you use simply typed lambda calculus over these data types, okay? And then apart from that, you keep the old functions that we had before. And there's one extra function, which is sort of this squaring function, which is I call split. And what it does is it inputs a list and it splits it into all possible ways of splitting into two parts. Okay, so this is the class of functions that we're dealing with. Maybe let me give you some examples in Haskell. So let's say that I want to go ahead. Sorry.
I was just going to say you have 5 minutes.
Sure, that's fine. I have to do my program. Huh? So I want to do a normal type of squaring. So it would be something like I input a list, and then for every position, I replace that position by the list itself. Okay, and then I concatenate the resulting list. Okay. So here I've used lambda abstraction in a non-trivial way, okay? And map. Map is one of the combinators that I have. And let me hope that it's correct. So this is a squaring function without the underlines. So I almost get squaring just automatically as a result of lambda calculus, but I don't get these underlines. And to be honest, I think that the split function, which has these underlines, is actually needed. So then you can start programming here. And I think it's a rather expressive programming language. And here is my proof. So at some point, my wife said, teach me some programming language. And of course I said Haskell. You know, she's a graphic designer, so clearly she needs to learn Haskell. And then I gave her, like, I mean, it was a biased sample, I guess, but there were all sorts of programs, and that just to train, and all of them were actually in this class, because you can go quite far. It doesn't have a Haskell recursion, true, but actually in many interesting string manipulations, the full power of Haskell of recursion is not needed. You can go quite far. I mean, very natural string manipulations can be performed this way. I mean, there is a certain amount of recursion in the fact that you have map, but it's very well it's well isolated, and a result is that, for example, this result that I mentioned for regular functions, it's actually also true for polyregular functions, that if you want to, you have an input string and you want to compute the output string, then you can compute it in linear time. Okay, it has super linear size. So you can compute it in linear time in terms of the output size. And there's even stronger things that you can do, like in AC0, it's not stronger, it's incomparable. Or you can have constant time access to random access to every output position. And this is all because of these restrictions here. So I think I'll be, okay, let me not discuss the proofs. But let me just finish my talk with some, well, perspectives. So the main open problem is, for polyregular function, is the equivalence problem decidable? It is decidable for regular functions, depending on how your device is given. It's in P space. For example, if the input is given as a two-way automaton. So for polyregular, is it decidable? We don't know. There is some recent work by Gaëtan Douaneau-Tabot who shows that it's decidable. It's already a non-trivial case if your output alphabet has one letter. So in this case, it's more like a string to number function. But already that is not clear, and the algorithm is like non-elementary or something. Okay, there is another result that I want to mention. This is by Nathan Lott, which explains very clearly and beautifully the relation between polyregular. So if you're linear, then you're polyregular, because it's designed to be an extension, and you have linear size increase. But the opposite implication is also true. So that's exactly what you get. It also goes to quadratic, but then you have to explain what that means. And then there's another line of work, which I think is very interesting. This is by well, Tito and Pierre Pradic, where they explore connections with lambda calculus, but in a different way. It's a different lambda calculus than my lambda calculus, because but with linear types in the sense of linear logic. And they study certain classes of subclasses of polyregular functions, which is called comparison free. And that means that if you, it's easiest to explain in the k-pebble case. You have k-pebbles, but you're only allowed to see the topmost one. That's what you can do. So that, I think, is all I have to say today about polyregular functions. Thank you for listening.
Thanks, Mikołaj. I'm gonna try to unmute everyone so that we can clap for Mikołaj. I think everyone can unmute themselves. Okay, so now I muted everyone again. Mikołaj, don't forget to unmute yourself. Any questions? Please raise your hands on the participant list, or put them on the chat. That's also okay. So there's a question by Tom Irshowitz. Tom, do you want to go ahead?
Yeah, thanks. Hi.
Hi.
I was wondering whether you have a proof that you need lambda abstraction, because you added split already. So does lambda abstraction really add something on top of that?
I don't, because it's not true.
I was suspecting this. Okay, thanks.
So in fact, there is a combinatory version without lambda abstraction, and it is equivalent. Yeah, it depends on what you want. I mean, as a programmer, I prefer to have lambda abstraction.
Sure.
But it turns out that it can be eliminated. Yes.
Thank you.
Ankit?
Yeah, I had a question. Can you represent block, which was shown in one of the earlier slides, using the lambda calculus syntax we have now?
Yes, that is true. So once you add lambdas, then that gives you a certain amount of extra power, and as a result, actually, for a block you can eliminate. Let's eliminate reverse. I think this was meant to be one of my my examples. So let's say I want to reverse this list. What I can do is I can split it, and then I can, I guess, take the second coordinates, and then I'm almost there, because now I need to apply the head operation to every second coordinate. My head is a special version of the head, which does error handling in the sense that it uses the empty list instead, which is kind of useful, because error handling is a nightmare in this program language. And then you can do concat it, and then you get the reverse of the list. So that's, for example, you can eliminate reverse, but you're right, you can eliminate block as well.
What I was trying to understand is how would you identify sigma, or how would you differentiate sigma from tau? Like, is there a recognizer to differentiate element types in the list? So if the list is composed of ones and twos and also characters.
So what you have every, yeah, did I mix something up? I guess I forgot one thing that if you have a, maybe it's not derivable. If you have a finite set, then you can split it into 1 plus 1 plus 1 plus 1 in as many times as and I guess I forgot to write that one. That's correct. So another way of saying it is every function with a finite domain is okay. So if you're, but I don't remember if this can be derived, and if not, then you just add that. That's a relatively finite. So thanks for pointing that out.
Okay.
Okay. I will stop the recording now, and then we can have informal discussions.
And now we get the hardboard question.